Because look, if I just give you r, I can't tell you what z is, right? I have to give you r and s. So in order for me to talk about how much z is changing, I'm going to have to hold one of these constant, right? I either hold the s constant or I hold the r constant. Those are the two that are possible. Let's draw the pieces of the tree here. Down this branch, what derivative goes down this branch? Partial, right? Why is it not dz dx? Why is it partial of z with respect to x? There are two other variables, so you'd have to hold these constants to take that derivative, right? Okay, let's keep going down this branch. How about down this side? What derivative is this? Partial x with respect to r, because you would have to hold this one constant. What about this branch? Partial x with respect to s. See what I'm doing? I do that for the rest of the tree. Here to here, partial z respect to y. Down these branches, partial y respect to r, partial y with respect to s. Partial z with respect to w, partial w with respect to r, partial w with respect to s. Yeah? These are all partials because on every kind of level of this tree, you've got multiple variables. All right. Now, how do we figure this out? Any guesses? If we do this, we're holding what variable constant? S, right? We're going to hold S constant. Okay, so to figure out what it is, let me highlight down here. These are my R's, right? If we hold S constant, think about this for a second. If we hold S constant, what's this? Should be 0, shouldn't it? What's that? What's that? 0. So to figure this out, what we're going to do is we don't have to go down this branch and both branches, this branch and both branches, this branch and both branches. We only have to go down the branches that lead us to R. So I'm going to take this, times this, right? Add to it this times this, add to it this times that. And that will be partial z with respect to R. So this will be partial z with respect to x, partial x with respect to r, plus, now the next branch, partial z with respect to y, partial y with respect to r. Last branch, partial z with respect to w times partial w with respect to r. I'm not going to actually calculate this, okay? But let's just talk through it. I mean, like I'm not going to write it down. What's the partial of z with respect to x? So here's z, partial of that with respect to x, 2xy. What's the partial of x with respect to r? 1, right? Treat that's like a constant. What's the derivative of r? 1, so that's a 1. Partial of z with respect to y, we've done that. What's that?
X squared.
X squared. Partial of y with respect to r? S cubed, good, S cubed. Am I going fast? No? You all right? Okay, okay. Plus partial z with respect to w? Negative 1. Partial w with respect to r? 2r. There you go. Make sense? Then you'd have to get each one of those, right? Get them all to what? R's? R's and S's? Yeah, you get them. It's okay if you had S's in there, but it would be down in terms of the last two variables. Okay, next one. So how do we do this next one? Same thing, but I've got to go down to get to the S's this time, right? So I would have what? This, and then this, right? Go down this way, this, and then go down here, and then this, and go down this way. You're just following the branches down to the variables, from the z all the way down to the s's. Anything that branches off to r, you know you don't have to worry about because you're holding r to be a constant. So this derivative is going to be 0. It's going to just go away. All right, I'll write it down just to be thorough. It's going to be partial z with respect to x, partial x with respect to s, partial z with respect to y, partial y with respect to s, plus partial z with respect to w, partial w with respect to s. Ooh, made one, finally. All right, I'm not gonna calculate that. You get the idea, yeah? Okay. Can I just add something to this now? Yeah? Same problem up there. R is, let's see, what have I not used? Let's just do this. R is a plus 1, and s is a cubed. Now what have I done? Is that the same tree? There's one more thing though, right? What does R depend on? A. What does S depend on? A. What does R depend on? A. What does S depend on? A. What does R depend on? A. What does S depend on? A. How many derivatives are possible? Just one. Because ultimately Z depends on what? A. So when I say what derivative is possible, what do I put here? Partial or no? No, not a partial. It's a regular derivative because if you know what A is, you know what Z is. You don't have to hold anything constant, right? So dz dA will be. So how do we do that? Now we're going to do them all. So we got to go down all branches. So I've got to first put these. What's this to here? Is it partial? It's just dr dA. This one ds dA. dr dA, ds dA, dr dA, ds dA. So now we've got to go down all branches. We got to go down here, plus, down here, plus, down here, plus, down here, plus, down there, plus, down there, plus. Right? No, that's it. That's the end. That would be it, right? So you can imagine, I mean, this generalizes, right? This generalizes. But it's a method, right? It's a method. It's a nice little, picture. I'm not going to write it down. Is that all right with everyone? I want to show you one more example that's confusing, all right? I hope this wasn't confusing. The reason we do this tree diagram is because it makes it a lot easier to deal with mentally. Doesn't it make this look pretty simple now? Like y is sine of x squared. I mean, like now it's just y, this is x, this is just dy dx, right? Like this is what we've been doing in the past. All right, so here's what I want to do. Let's do z is equal to x plus y squared plus w to the third. Okay, make that kind of nice for you. I'm going to say that x is equal to r minus s squared. I'm going to say y is equal to r plus t squared. This is where things can get a little bit weird. Do y'all see why this one's weird? Oh, wait, I forgot my w. Yeah, because w doesn't equal anything. W is, let's go with r times s. Sorry, I forgot that one. I could have left it out, but I'll put it in there for you. All right. So what do you need in order to know what z is? X, y, and w. So let me put that over here. Z, I need x, I need y, I need w. All right, what do I need in order to find out what x is? R and S. R and S. What do I need to figure out y? R and T. And then W? R and S. What's different? We have this T here, right? So the way that we're going to deal with this, any guesses? Let me go back to this one right here. What does x depend on? R and S and t. You just don't see it here, right? Now does it depend on t? Yes. So I could act like this depends on t, couldn't I? But it's just like 0t. And then this one depends on r and t, but you could also say it depends on s, right? 0s. So I could put that s in here, right? Like that. And then this one just needs to depend on t, right? So I could say plus 0t. Do you see how that's kind of like a clever way to make them all depend on the same thing? What derivatives are possible here? 3 different ones. Partial z with respect to t. I could do partial z with respect to r, partial z with respect to s, right? Those are the 3. I'm only going to do, well, maybe we'll do more than one. Let's draw it. Let's do this one. So what I need to do is I need to go down the branches that get me down to the t's, right? So that'll be, oh, I didn't put them in here, sorry. From here to here, partial z, respect to x, this one partial z, respect to y, this one partial z, respect to w. These are all partials too, right? Partial x respect to t, partial x with respect to r, partial x with respect to s. And then do I have to do them more? Can I leave out? Okay. All right, let's go down the branch. We need to get down to t, right? We need to get down to t. That's here, here, and here. Okay. So this is what? This one? That marker's no good. I don't know. Maybe it'll work. Maybe this one's better. No? Partial z. That's really light, huh? It's okay? I'm going to go with black, just so y'all can see it. So that's that one, right? And then what? Partial x with respect to t, right? Plus partial z with respect to y times partial y with respect to t plus partial z with respect to w times partial w with respect to t. But
what if the dz, like dx dt, or partial t with respect to t, partial x with respect to t be 0?
Exactly, right? Do y'all see that the things I added here, this x, when we get to x and I say, what's the partial of that with respect to t, what would you say? 0. So isn't this going to be a 0? Which is going to kill that off completely. Are there any others that are going to be 0? This one right here. W with respect to t, right? What's the derivative of this with respect to t? 0, right? So that's going to kill this off. So it winds up at the end of the day only being this, right? Only this one. See that? Okay. And then we could do the other 3, or the other 2. Yes?
Question. As soon as it's a multiplication of fractions, can we multiply the whites and then the answer will be partial c with respect to t?
Wait, say again?
If you, so you multiply two fractions. Can you, for example, on the middle one, can you delete the whites and partial c with respect to t? Should be answered.
Well, but if you cancel these, right, you're saying partial z with respect to t. Now you're coming back over here and you're saying, what's the derivative of this with respect to t? You don't see any t's here, right?
Oh.
Because you would have to first replace x with this, y with that, w with that, and then you would have t's in here.
Okay.
So no, don't cancel these.
Okay.
Let's just, can we verbally say what this next one would be? What would be the first piece of this one? Partial z with respect to x, then partial x with respect to r, plus partial z with respect to y, partial y with respect to r, plus partial z with respect to w times partial w with respect to r. Do any of those become zeros? None of those would become zeros, would they? Because when you go down here, right, that wouldn't be a 0. Come down here, that would not be a 0. And then down here, that would not be a 0. All right, we're going to move on. if that's okay with everyone. You know what? Where are the mini exams? Those extras? Can I see those? Take a look at the next mini exam for a moment. Let's just look at this one, because this is due actually, your mini exam 3, right, is due next time we meet on Wednesday, right? This one is due a week from Wednesday. So I'm not giving you a whole lot of time, but actually you can do this entire thing right now. Like in theory, you could do it. First one, I give you a function, 2 variables. I ask you to find the domain and to sketch the domain. We did that in class, okay? If you want, you can use like graphing software if you want to, like, you know. Remember I sent you all that email? I hope that came across right. I wasn't like getting on y'all. I was just, did y'all get that email where I sent one of your classmates' exams? Just kind of give you an idea, okay? I mean, put pictures in there. You know, go to some graphing software, graph it, copy, paste, put it in there, you know? Okay, but you still have to solve it. You have to solve it algebraically, right? What's the domain of that function? Number 2, I give you a function of 2 variables, x and y, and I ask you for these partials. What's partial with respect to x? What's partial with respect to y? What's partial with respect to x, then x again? What's partial with respect to y, then y again? Right? That's all very mechanical, yeah? Number 3, really that number 3 is just to make sure you understand what that notation means. Obviously it's a third derivative, but what order do you go in? Don't tell me. Is it x then y, or is it y then x? I'm not telling you. You go figure it out. It's in the notes, it's in the ebook, you can figure it out, and I talked about it in class. Number 4, okay, that one I take it back. That one you cannot do until what I'm about to give you. Oh wait, no, sorry, you can. You can do that. But you can do it 2 different ways. You can do it the way I've already shown you, or you can do it with the thing I'm about to show you. Number 5 is very similar to what I started class with. I give you a function, I give you a point, you find the equation in tangent plane. And then number 6, that's the tree, right? What derivatives are possible? Draw a tree diagram, label all the branches, find a formula for each possible derivative, and then actually find the derivatives. I mean, do y'all see what I'm saying? This should be a pretty straightforward mini exam. I mean, some of the computations might suck and that things are going to get long and ugly, but as far as like really having to think outside the box, I don't think it's there in this one. And do you remember me telling you all at the beginning of the semester that as we move on in this class, the mini exams will become more mechanical? They will start to look more like homework problems. So just keep that in mind. All right, we are continuing, same section, okay, same section. Where is it? Where the hell is it? There it is. All right. So this is like my notes just showing the same sort of thing and giving some examples. You know, there's only one possible derivative in this tree because everything depends on t, right? If you have, you know, if your bottom has 2 different variables, then there's going to be 2 different partials, and so on and so forth. And then we get to implicit differentiation. So what we're doing is we're going to somehow try and use this concept to do implicit differentiation, which is something we did earlier last class. So I'm gonna leave these notes up here, and then I'm gonna write down on the side like an example, all right? So let's say that z is equal to some function of 2 variables. Let's keep it simple. Let's go x squared y plus xy squared. Let's just go with something like that. Do y'all agree z is a function of 2 variables? Yes? Now this is nice because right now z depends on these 2 variables. Everything's great, right? But we're going to rewrite the equation by moving this function of 2 variables over to the other side. Z equals, not equals, I meant to say z minus x squared y minus xy squared. Let's do it this way. Let's put plus there, and let's put a parenthesis. Okay, just so we see that what we're doing is we're doing z minus f of xy, right? That's this. Do you all agree I could do that? Nothing wrong with that? Okay, and now from this, I'm going to take everything that's on the left-hand side, everything that's here, and I'm going to say to you, hey, look, do you all agree that that is some function capital F of 3 variables now? I could call the left side of that some function of 3 variables. It depends on z, depends on x, and depends on y. So capital F depends on 3 things. That's what this is saying here. So then capital F is really f of x, y, z is a function of x, y, and z. Also, we need to keep in mind that the z, we know z depends on x and y, right? But the x and y may also depend on each other. Now that's not going to be immediately clear, but let me continue. Now what we're going to do is we're going to take this equation, right? Do you see this equation we have here? And we're going to do implicit differentiation. Okay, we're going to do implicit differentiation. So before I do it, f depends on what variables? X, y, and z. Do you all agree with that? This capital F depends on x, y, and z. So right now, just off of that, what derivatives are on that tree? Partials, right? It's partial of capital F with respect to x, partial capital F with respect to y, partial capital F with respect to z. Y'all agree that that's just the 3 parts of that tree? Yeah? Okay. We know that z depended on what? X and y, didn't it? So I'm going to continue this tree, and I'm going to say, hey, that z depends on x and y. We know that because of this, right? Z depends on x and y. So now down that tree, that branch right here, I have those branches. I have partial z with respect to x, partial z with respect to y, right? Y'all still with me? Trying to think of how I want to explain this. I'm trying to get down to the point where I can ask you what derivatives are possible. Okay? What derivatives are possible? Would you be okay if I wrote this? Could you say that x depends on itself? Like if I know the value of x, I know the value of x. Even though it's weird, could I do that? Yes? Could I do the same thing for y over here? That's not too crazy to think of, right? If I know y, do I know y? Yes. If I know x, do I know x? The thing is, I'm trying to get everything down to the same 2 variables at the bottom, x and y. Would it be okay for you if I did this? I'm going to put them a different color because they're kind of this is kind of a head scratcher moment. Oops, sorry, that should be x. All right. So if you're over here, right, and you're going down this branch, right? If you're going down this branch, what are you holding constant? Right? What are you treating like your variable? X, right? So you're holding z and y constant. So if z and y are constant and you know what y is, then could you determine what x is? Look at this equation right here. If you were holding z and y constant, could you tell me what x is?
Yeah.
Yes? Imagine z is some constant and y is some constant. Then do you know what x is? So could you argue that when you're down this branch, that if you're holding z and y constant, then x will depend on y. You give me y, I could give you x then. Yes? Similarly, if you're down this branch, you're holding x and z constant, then if you give me x, I should be able to give you y. So even though it's weird to write it that way, that is not wrong to write it that way. And that allows me to finish this tree out. That's where this is saying also x may depend on each other, right? X and y may depend on each other. So let me fill this out. This is going to be what? Partial x with respect to x, partial x with respect to y, partial y with respect to x, partial y with respect to y. I know you're like, what in the world are we doing, right? What derivatives are possible? There's two. What are they? Okay, yep, let's write it down. So one of the derivatives is partial capital F with respect to, let's go x first, right? And what is that? It's kind of weird. Go down this. Okay? I know that looks weird, okay? Just keep going. Plus? Partial f, y, partial y, x, okay? Plus partial f with respect to z, partial z with respect to x. Right? I know that looks weird. Just hang with it for a minute. Okay, what is this? 1. Okay, that's nice, right? That's 1. Okay, if that's 1, then can't I subtract this on both sides? I know it looks weird, but just if that's a 1, this becomes 0 because I can subtract that, and this is partial f with respect to y times partial y with respect to x plus partial f with respect to z times partial z with respect to x. Yes? Okay. What are we doing? All we're doing is just saying, can we do this, right? Can we do this? Trying to see if, let me go back for a second. When we started this, it was this, right? To take you back to this, right? That's what we started with. And then I moved something over, I called it capital F, and we created all this table, right? Okay, so, did you raise your hand?
No.
Okay. I'm trying, just give me a second. I'm a little hung up because I want to draw what we're trying to achieve here, but I don't want to confuse you, but I think I'm going to. In the beginning, we had this, right? In the beginning, we had this. What are the two derivatives that are possible here? If z depends on x and y, the only two things are partial z with respect to x and partial z with respect to y. Those are the only two. And we find them by going back to this right here, right? To find partial of this with respect to x, we hold y to be constant, we take derivative, right? And then if we do it the other way, we hold x constant and take derivative, right? And then we start moving all this stuff around, doing all this, and we get down to this, and we get down here, right? To this piece right here. And what I'm trying to get to is this piece right here. Do y'all see it right there? Do y'all see that right there? That is one of the possible derivatives. Can we solve for that here algebraically? How would you solve for that? Get this by itself. Okay, you'd have to move this over to the other side, right? Okay, partial f with respect to y. I'm subtracting. And then partial y with respect to x. That would move that over. And now what? Divide that by partial f with respect to z, and that would be equal to the partial z with respect to x. You all okay with that? So what I was trying to do, the reason I was like saying I'm hung up here a little bit is because I'm trying to get you to see why I want to solve for this. I want to solve for this because I wanted to see if I could find a formula for going down this branch. I understand that me moving everything over and all that doesn't seem like a very natural thing to do, all right? But if you agree it allows me to solve for this, then there it is, right? Now, I want to show you what the final answer is to this. We have a formula for it, but I want you to see the formula here. Where is it? Okay. This right here. This is, I'm going to write the formula right here, and then I want to see if we can get to it. So the partial z with respect to x equals negative partial f with respect to x over partial capital F with respect to z. Is that what we have? Let me get this out of here now. Is that what we have?
Yeah.
How? You got to convince me.
On the top, you got the partial y. Just you have the partial capital F over partial y times partial y over x. In respect to x, so those partial y's will cancel out. So then you're left.
Essentially, this is the same as what's up there.
Yeah.
Yeah.
Okay. So these two kind of go, and you have that. All right? This is the big takeaway. All right? You don't need to know this whole process. This is the big takeaway that we're about to use in a moment. All right? Now, that was me, I erased the tree, but do you remember that was me just going down the x's? We could do the y's the same way. And if we did the y's the same way, we would get a different formula, and the formula would be almost the same as this. So that's going to give me this one right here. It would be, it's still negative, partial f, but this time with respect to y over partial f with respect to z. The only difference between the two formulas is that. Okay? And these are in the notes. These two formulas are in the notes. All right? Now, again, why in the hell would I ever do that, right? Why in the hell would I move everything over? Well, look, this is an example right here. This is the example. Let's find these two partials.